Okay, let's do our next example. You are traveling 3 kilometers upstream to a taco truck on the other side of a 1 kilometer wide river. You can run 6 kilometers an hour, but you can only row your boat 2 kilometers per hour. What path should you take to get tacos as soon as possible? Something I ask myself all the time. So let's go ahead and draw this out. See if you can draw it out yourself first, but it does help to see what this looks like ahead of time. So you've got a river, whoop, whoop, and there is some kind of a taco truck. Tacos. Okay, and you want to get there, and this example is a classic example. It's going to look a little bit like this. You're taking a path, and you're going to row your boat, and then you're going to run to tacos. It is not always tacos, of course. Believe it or not, if you're doing something like Snell's Law for the path that light travels, you end up doing the same optimization problem. So we need to label some things, get some variables here. The main issue that we want to find out is, okay, where should I land? Where should I aim for? Where is this point right here? Okay, once I know where that point is, I know where to aim my boat, and then from there I'll run. So to describe that, as a modeler, I need to come up with some variables here. Let's just call this variable right here, I don't know, d for distance. Okay, if I know d, I know my whole path. So let's go ahead and label a few more things here, just to get it all across. This is a 1 kilometer wide river. Okay. Just so you know it's a river. Bloop, 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 bloop. Right. And the length of the whole darn thing to the taco truck, it sounds like, is 3. So somehow we've modeled this entire problem with just a single variable. That's pretty incredible. It's possible that if you went to do this the first time, you might have had more variables and had to solve for it. There's often more than one way through this, but as you get a little better, you can do it with fewer and fewer. Okay, from here, let's go ahead and figure out what am I optimizing. And here's where things get a little bit tricky, I think. We're going to optimize time. How long does this take? Which means we need a formula for how long it's gonna, how much time it takes. So t is equal to, and we're gonna need to think through this. So if that is d, then that means this thing up here is 3 minus d. Okay, so we're gonna run for 3 minus d seconds. Sorry, 3 minus d kilometers. Okay, so if I run for 3 minus d kilometers, how long will that take? Let's do a little bit of unit analysis here on the side in case you're not familiar. So 3 minus d kilometers times how fast do I run? That would be 6 kilometers per hour. Okay. Notice this doesn't quite work out if I try to multiply it. I don't really want to multiply. I want to get something in hours. So in fact, what I need to do is I need to divide. Okay, so it's really 3 minus d kilometers times 1 hour per 6 kilometers. All right, that might seem a little weird at first. We can write this more generally, which is that distance over speed is going to be equal to time. So time times speed is distance. Distance over speed is time. So you can do a little bit of unit analysis to help yourself out if you want, or you just think about it. If I want to go 5 miles and I'm going 2 miles an hour, how long will that take? 5 divided by 2. Okay, so we want to divide by speed. So I want to divide by 6. Okay, that is how long that second part takes me. Let's do the first part now. I need to know how far I'm rowing my boat. Well, that's a right triangle. So up here, this looks like the square root of 1 plus d squared. Using Pythagoras, a squared plus b squared is c squared, and I solve for c. So this becomes the square root of 1 plus d squared all over, how fast can I row my boat? 2. Whew. All right. From what I remember of the first time I saw this, I probably would not have been able to get that far on my own. So take a second, make sure that makes sense, and then see if you can finish the problem from here before watching me. I'm going to continue on. This looks great because I only have one variable. All the constraints are kind of baked in, so I don't need any constraints to reduce it. I've gotten all the information from my problem into this. Let's go ahead and find, what am I finding? Not the maximum, but the min. How do I do that? I take the derivative. This is going to look really funny. I did this a little bit on purpose. dt dd. That is true. That is correct. Fun note for yourself, maybe don't pick lowercase d. Maybe do an uppercase d. Maybe do something else. But we're going to keep rocking with this because I like to show you how weird things can look sometimes. Now let's go ahead and take the derivative with respect to d. That divided by 6 is really a 1/6. That can stay on the outside. The derivative of 3 minus d is just -1. How nice is that? Plus, that divided by 2 is just a 1/2. That can hang out up front. And now I need the derivative of this square root. So if I recall, the derivative of a square root is going to give me another 1/2 times 1 plus d squared to the -1/2. I have to do my chain rule times 2d. Many correct ways of writing this. You might have written this as 1 over 2 square root of 1 plus d squared. But don't forget that chain rule for that d squared. Okay, Fermat's theorem, finding that critical number, we're going to set this equal to 0. I'm going to clean up the right side a little bit. This looks like -1/6 plus 1 1/2. 1/2 times a half times 2 is a half. D times 1 plus d squared to the -1/2. Okay, can you solve that? Maybe. Let's go ahead and try to solve this. I'm going to bring that 1/6 over. Okay, I'm going to go ahead and multiply both sides by that 1/2 to get 1, or by 2 to get 1/3, and get rid of that 1/2. And then I'm going to also play this game where I multiply both sides by this 1 plus d squared to the 1/2. So I would get 1 plus d squared to the 1/2 equals d. Not bad. What do I do now? How do I solve this? I'm going to go ahead and square both sides. I suppose I could have done this a step before too, but I'm going to square both sides here. I get 1/9 times 1 plus d squared equals d squared. Okay, now it's a quadratic. Can you solve this? Can you solve it? Let's go ahead and move over here. Looks like 1 plus d squared equals 9d squared. 1 equals 8d squared. 1/8 is equal to d squared. D is equal to the square root of 1/8. By the way, that is also equal to 8 to the -1/2. Cool. By the way, our units in this case is kilometers. That was a nice reminder on solving things like this. There's often some solving that you have to do. But just check, does this make a certain amount of sense? The 1 over the square root of 1/8 is less than 1, which kind of makes sense. These numbers up here are pretty small, right? This is 3, this is a 1 here, and so we're going to go, less than 1/3 of the way up. We're going to take a pretty sharp angle there to cut across, and this is what you should expect to happen whenever you have to use a slower medium for part of the way, is that you want to kind of cut that corner. I think about this a lot when I'm crossing the street. Maybe I can cut a corner to save some overall time. again, it shows up in lots of neat places like calculating the route that light takes, because light always takes the fastest way places. So when it's going through a lens, this is exactly how you can figure out the angle of refraction. Otherwise, this is also a really standard calculus problem. So hopefully it's a little neat once you get over the algebra I made you do at the end. I'll see you all next example.